Hello everyone. Today shall discuss about real numbers and their decimal expansions. In this section, we are going to study rational and irrational numbers from a different point of view. We look at the decimal expansions of real numbers and see if we can use the expansions to distinguish between rationals and irrationals. We'll also explain how to visualize the representation of real numbers on the number line using their decimal expansion. Since rationals are more familiar to us, let us start with them. Let us take three examples: 10 by 3, 7 by 8 and 1 by 7. Pay special attention to the remainders and see if we can find any pattern. Find the decimal expansion of 10 by 3, 7 by 8, 1 by 7. 10 by 3, it is 3.3333. Repeating, and 8, 7 by 8, we are getting 0.875. The remainder is 0. 1 by 7, that is 0.142857. Remainders is 11111 divisor 3, remainders 640 divisor 8, remainders 32641, 32641. It is repeating, divisor is 7. What have you noticed? You should have noticed at least three things. The remainders either become 0 after a certain stage or start repeating themselves. The number of entries in the repeating strings of remainders is less than the divisor. In 10 by 3, one number repeats itself and the divisor is 3. In 1 by 7, there are 6 entries, 3, 2, 6, 4, 5, 1 in the repeating string of remainders, and the 7 is the remainder. In the remainders, if the remainders repeat, then we get a repeating block of digits in the quotient. For 10 by 3, 3 repeats in the quotient, and for 1 by 7, we get repeating block of 142,857 in the quotient. Although we have noticed this pattern using only the examples above, it is true for all rationals of the form p by q, q is not equal to 0. On division of p by q, two main things happen: either the remainder becomes 0 or never becomes 0, and you get a repeating string of remainders. Let us look at each case separately. Case 1, when the remainder becomes 0. In the example of 7 by 8, we found that the remainder becomes 0 after some steps, and the decimal expansion of 7 by 8 equals 0.875. Other examples are 1 by 2, 0.5, 639 by 250, 2.556. In all these cases, the decimal expansion terminates or ends after a finite number of steps. We call the decimal expansion of such numbers terminating. The remainder never becomes 0. In the examples 10 by 3 and 1 by 7, we notice that the remainders repeat after a certain stage, forcing the decimal expansion to go on forever. In other words, we have a repeating block of digits in the quotient. We say that this expansion is non-terminating, recurring. Then 10 by 3, 3.33333, or 1 by 7, 0.142857, 142,857, 142,875. The usual way of showing that 3 repeats in the quotient of 10 by 3 is to write 3.3 bar. Similarly, since the block of digits 142,857 repeats in the quotient of 1 by 7, we write 1 by 7 as 0.142857. With the bar above the digits indicates the block of digits that repeats. Also 3.57272 can be written as 3.572 repeating. So all these examples gives us non-terminating repeating decimal expansion recurring, or non-terminating but repeating decimal expansion. Thus you see that the decimal expansion of rational numbers have only two choices: either they are terminating or non-terminating recurring. Now suppose, on the other hand, on your walk on the number line, you come across a number like 3.142678 whose decimal expansion is terminating, or a number like 127,270, that is 1.27 bar, whose decimal expansion is non-terminating recurring, and can you conclude that it is a rational? The answer is yes. We will not prove it, but illustrate this fact with a few examples. The terminating cases are easy. So that 3.142678 is a rational number. In other words, express 3.142678 in the form by q, where p and q are integers and q is not equal to 0. Solution: where you have 3.142678, 3142678 by 1, 0, 0, 0, 0, 0, 0, and hence it is a rational number. Let us consider the case when the decimal expansion is non-terminating recurring. So that 0.33333 or 0.3 bar can be expressed in the form p by q, where p and q are integers and q is not equal to 0. So you do not know that 0.3 is, let us call it x, and so x equal to 0.3333. Now here is where the trick comes in. Look at, if you multiply both by 10x by 10, then we are getting 10x, 10 into 0.3 or 3.3333, or you can write 3.33 as 3 plus x, since x equal to this. Therefore 10x equal to 3 plus x, or solving for x, 9x equal to 3 or x equal to 1 by 3. So that 1.272727 bar can be expressed in the form p by q, where p and q are integers and q is not equal to 0. Let x is equal to 1.272727. Since the two digits are repeating, we multiply x by 100 to get 100x is equal to 127.2727. So we can write 100x is equal to 136 plus 1.2727, that is 136 plus x. Or 100x minus x is 126, 99x is equal to 126. Or x equal to 126 or 99, that is 14 by 11. You can check the reverse, that 14 by 11 equal to 1.27 bar. So that 0.235353 can be expressed in the form p by q, where p and q are integers. Let us equal to 0.235. Over here, note that 2 does not repeat, but the block 35 repeats. Since the two digits are repeating, we multiply x by 100 and get 100x equal to 23.53535. 100x equal to 23.3 plus 0.2335, that is 33.3 plus x. 99x equal to 23.3, or 99x equal to 233 by 10, which gives x equal to 233 by 990. You can also check the reverse, that 233 by 990 equal to 0.235 bar. So every number with a non-terminating recurring decimal can be expressed in the form p by q, where p and q are integers. Let us summarize our results in the following form. The decimal expansion of a rational number is either terminating or non-terminating recurring. Moreover, a number whose decimal expansion is terminating and non-terminating recurring is rational. So we now know that the decimal expansion of a rational number can be. What about the decimal expansion of irrational numbers? Because of the property above, we can conclude that the decimal expansion are non-terminating, non-recurring. So the property of irrational numbers, similar to the property stated above for rational numbers, is the decimal expansion of an irrational number is non-terminating, non-recurring. Moreover, a number whose decimal expansion is non-terminating, non-recurring is irrational. Recall is 0.10110111011110. The previous section, notice that it is a non-terminating, non-recurring. Therefore, from the property above, it is a irrational. Moreover, notice that you can generate infinitely many irrationals similar to S. What about the famous irrationals root 2 and pi? Here the decimal expansion up to a certain stage. Root 2 is 1.41421356 and pi equal to 3.141592, etc. Note that we often take 22 by 7 as an approximate value for pi, but pi is not equal to 22 by 7. Over the years, mathematicians have developed various techniques to produce more and more digits in the decimal expansion of irrational numbers. For example, we might have learned to find digits in the digital decimal expansion of root 2 by the division method. Interestingly, in the Cbse Rules of Chord, a mathematician treatise of the Vedic period, 800 BC to 500 BC, you can find the approximation of root 2 as follows. Root 2 is 1.4142156. Notice that it is the same as the one given above for the first 5 decimal places. The history of the hunt for digits in the decimal expansion of pi is very interesting. The Greek genius Archimedes was the first to compute digits in the decimal expansion of pi. He showed 3.140845. Pi lies between 3.142857. Arjavetta 476 to 550 CE. The great Indian mathematician and astronomer found the value of pi correct to 4 decimal places 3.1416. Using high-speed computers and advanced algorithms, pi has been computed to over 1.24 trillion decimal places. Now let us see how to obtain irrational numbers. Find an irrational number between 1 by 7 and 2 by 7. We saw that 1 by 7 is 0.142857. So we can easily calculate 2 by 7, that is 0.285714. To find an irrational number between 1 by 7 and 2 by 7, we can find a number which is non-terminating, non-recurring lying between them. Of course, you can find infinitely many such numbers. An example such a number is 0.1, 0.1, 50, 1500, etc. Dear friends, if you like this video, please subscribe, like and share. Thank you everybody for watching this video.